Welcome back to Applied Mathematics. In this video, I'm going to be talking about higher order systems. We've already talked about systems of equations. We've already solved systems of equations, and we've already seen how systems of equations can be useful. A higher order system is a system in 3, 4, 5, 20, 5,000, or some other number of variables other than 2. The process of solving a higher order system is do work to make it look like a lower order system until you can get it down to a planar system, and we already know how to solve a planar system. So without further ado, let me get my head out of the way and let's dive right into an example. All right. 3x plus 2y minus 5z equals 5. 2x minus 3y plus z equals negative 1, and x plus y minus z equals 3. Same process we've talked about before. I'm going to be using the method of elimination. None of the equations are solved for a variable, so trying to use substitution is going to be very painful and I don't want to deal with it. So let's go ahead and name all of these equations. I have 3 equations and 3 unknowns, so I do expect that there should be a unique solution, but we'll find out. In the method of elimination for a higher order system, we're going to choose one of the variables and eliminate it not once, but twice. We'll choose one pair of equations and eliminate that variable, and then we'll choose a different pair of equations and eliminate the same variable. In this particular case, I'm going to eliminate z first of all, because I notice right away I've got plus z and minus z, and if I just add equations b and c together, those are going to get eliminated. So I'm just going to copy down equation b exactly as it is. I am going to add them together. 2x plus x is 3x. Minus 3y plus y is minus 2y. And negative 1 plus 3 is 2. Of course, z minus z is 0. The z's have been eliminated, which is what I wanted. And for some reason I wrote plus instead of equals here. I don't know why I did that, but let's correct that. Right. This takes me from an equation in 3 variables down to an equation in 2 variables, just x and y. This is something that I'm going to come back to a little bit later. So let's give it a name, just continuing the alphabet. That'll be equation D. I haven't touched equation A yet, so that is definitely going to be on my list next. Now I have a choice between the other equations. But I do notice here that A has minus 5z, and if I take equation B that has plus z, and I multiply by 5, those are going to be able to be eliminated as well. So I'll have equation A by itself, and then 5 times equation B. So I've got 3x plus 2y minus 5z equals 5. I've got, let's see, 2 times 5 is 10x. 2 times 3 is 15, so it'll be minus 15y plus 5z equals negative 5. Add these 2 equations together. It's going to give me 13x minus 13y minus 5z plus 5z is 0. And then on the right-hand side, 5 minus 5 is also 0. That's actually really convenient. I'll go ahead and name that as equation E. So now I have two equations that have x and y. I have taken my system of three equations and I have simplified it down to an equation in two variables. That's easier to solve. Actually, the first thing I'm going to do, I notice in equation E, I've got these factors of 13 that I really don't like. So let's go ahead and make a new equation F. Just divide both sides of that equation by 13, and we get x minus y equals 0. I could go from here and solve for x or for y and use the substitution method, but I'm going to stick with elimination just because that's what I said I was going to do. There's no wrong way to go about it. There's easier and harder ways. And I'm just going to stick with algorithmically, let's do this, then do this, then do this, instead of trying to find the most elegant approach for a particular situation. All right, but I've got equation D, 3x minus 2y equals 2. And then I can choose. I can either eliminate x or eliminate y. There's no wrong or right answer. I'm going to eliminate x, I think. So I'm going to subtract 3 times equation F. That's going to be minus 3x plus 3y equals 0. When I add these equations together, 3x minus 3x is 0, minus 2y plus 3y is 1y, or just y, and 2 plus 0 is 2. I get that y is equal to 2. Plug that into equation F. I have now x minus 2 is equal to 0, which I can rearrange and get that x is equal to 2. There's my second coordinate for the solution. Now I have to go back and find an equation that has z in it. They're off the screen, but I can scroll back up. I can choose any of these. There's no right or wrong choice. I think life will be just ever so slightly easier if I choose equation B here. I'm choosing that because it has z by itself with no coefficient, not even a -1. All right, so I'll copy that and paste it down here. I will plug in my values of x and y. So x is 2. My y didn't get copied for some reason. That's okay. My y is 2. So I've got 4 minus 6 plus z equals -1. -2 plus z equals -1. Or z itself is going to be +1. All right, x equals 2, y equals 2, z equals 1. For x, y, and z, it is reasonable to use what's called an ordered triple, x, y, z, just like the ordered pair is x, y. Once you get to higher order systems, or if you're dealing with a system that has particular variables instead of just x, y, and z, then how the ordered, we call it generally an ordered tuple, how that's set up doesn't have a standard, so just listing out all of the variables would be appropriate. But that's the basic idea. We can use the process of elimination to try to get down to having fewer equations in our system and having fewer equations in our system until we get down to something that is easily solvable. I do want to go through one other example in this lesson. This system looks intimidating. It's a system of 4 equations in 4 variables. A plus 2b plus 3c minus 4d equals 0. 3b minus 4c plus 5d equals 7. 2c minus d equals 1. And d equals 9. But wait a second. D equals 9. I've already got part of this solved. And not only that, but the rest of this is going to be incredibly straightforward. Because I can take that result of d equals 9. I can plug it into the earlier equation. 2c minus 9 equals 1, which means that 2c is equal to 10, and c itself is equal to 5. If I go back one equation earlier, 3b minus 4 times c, which is 5, plus 5 times d, which is 9, equals 7. And I get that b is negative 6. Plug all of that into the first equation. And I get that a is 33. I chose this particular example in a way that I think made it kind of apparent what was happening. This is a form that's known as triangular form. It's called that because we can draw a triangle of where the information is, and then there's a triangle worth of stuff that's missing. I could make this harder to see by shuffling the equations around. Maybe it's not in this nice order. Maybe it's, C first from equation 2. And then if you plug that into equation 4, you'll get the value of A. And then if you plug A and C into equation 1, you'll get D. And then you can go to equation 3 from there and get B. Right? Just shuffling things around, making it a little bit more obnoxious. But whenever you are missing pieces like this in the initial setup, which is a thing that can and will happen in real life, try to use it to your advantage. See if you can find an elegant approach to solve the system. Right. That's all I have for you on this one, so I'll wrap up with that. As always, thank you for joining me. I'll see you next time.